So when Anna asked me to give the talk, I thought I would give you a guide to where we are in various applications of electron interactions, particularly exciting time at the moment, and how Quantemol, I've got a few slides at the end to show what Quantemol can do. So it's going to be a very rapid run through, lots of nice pretty pictures, and then we go to lunch. Obviously, when we're talking about the roles of electrons interacting with molecules particularly, there's a whole range of phenomena, and obviously we've concentrated mainly this morning, because many people in the room, on plasmas, but we have to remember that there's a lot of other processes where this information is needed and where Quantemol and modelling and experiments are required. Atmospheric physics and planetary pictures, increasingly understanding the formation of molecules in space, and I'll show you some pictures of that, rather interesting astrochemistry. Obviously, we've got the semiconductor plasmas, we've heard lots of that. We also have lighting and the lighting industry, and we had a meeting with the lighting industry later on. We're moving away from these things. These are evil. These have got to go to these things. Tunisia was rather interesting. 40% of their electricity in Tunisia actually goes in lighting. So making more effective lighting is quite interesting. And an area where a lot of interest has been concentrated on in the last 10 years has been understanding that actually low energy electrons, electron interactions with the DNA and with the biomolecules is actually what leads to some of the breakup and damage of the DNA. It's the secondary electrons produced by the ionizing radiation. So we want to look at bigger and bigger systems. And finally, but perhaps also very excitingly in the nano world, we now have instruments like this, AFMs and STMs, which is effectively an electron device, and it happens to actually trigger chemistry by breaking up molecules on surfaces for a few years. So what do electrons do? How do they actually trigger some of the chemistry? Obviously, we've talked about them interacting and scattering, but what happens is that when the electrons interact with the molecules, they can excite them, and usually an excited molecule is more reactive than a ground state molecule. The molecule can be broken up and dissociate and produce radicals, and the radicals are usually more chemically reactive than the neutral. And of course, you can get ions, and you can then introduce ion reactions. So normally what happens, though, often when you get low energy electrons, and again, I think most people in the room have heard it, but for those who haven't, you go through some intermediate state, you get the reactions afterwards, and it's these things, as I say, which we often might call R, which do that. Now, one of the examples we could, for instance, look at is how do you make molecules in space, where you've got a lot of ionizing radiation, you've got ultraviolet light, and there's a lot of interest in that, in trying to see if out there in the stars there's a lot of rich chemistry, ultimately, which might explain how we got here. And for example, there's a molecule being looked for in space at the moment called glycine in the interstellar medium. In about 2003, there were various papers that came out saying, oh yes, it's there, and if you've got glycine, it's a building block of life. There. Well, resolution hasn't actually enabled us to confirm that, but we have a telescope coming online shortly called ALMA, which will be able to look for it. And you can do experiments in the lab to look under these conditions. We do them at the Open University, but there's a very big European network involved in this at the moment, where what people try and do is recreate the conditions in the interstellar medium, the dark regions between the stars. So what you essentially do is make yourself the best vacuum you can, which unfortunately is still about 1 million times more dense than the interstellar medium in space. You make it very cold, you get it down to temperatures of liquid helium, around about 10 to 15 Kelvin, and this mimics what happens in space. And then you hit it with something like low energy electrons, and you look and see what molecules you make by spectroscopy. And if you do that, and you make an ice and you irradiate it, and you irradiate ices of mixtures of molecules that you find in the interstellar medium, like carbon dioxide, methylamine, and oxygen, you get spectra like this, which tell you that electron-induced chemistry produces amino acids, which you can maybe find in space, and which ultimately might explain how life-bearing molecules were manufactured in the universe and maybe ultimately made us. Often they form these types of molecules not as neutrals, they make them as ions, but that's kind of regardless. So we can do a whole series of these electron-induced chemistry experiments, and we're doing them at the moment, I say, across Europe, where basically we take ice mixtures, we irradiate them with electrons, quite high energy, but it doesn't really matter, and we make molecules. And that's in a form of electron-induced chemistry, which is getting a lot of interest at the moment. You can make some rather interesting ones. You can make molecules like ammonium carbamate by mixing ammonia and CO2, hit them with some electrons, and as I say, you make it. If you don't want that one, you can make mixtures of ammonia and methanol, and you irradiate that, you make ethylene glycol. If you make methyl formate, and you can make formamide. So this is how electrons induce chemistry. You radiate some molecules, they break up, produce some radicals, and they react. And that's what we mean when we're talking about electron-induced chemistry. Okay. Finally then, so what's the role, why Quantemol is so important to this type of work is the applications are so vast that we need a huge amount of data. And the amount of data that we need is just far too, we've got data overload. We just can't measure all these things. We've got to be able to ultimately calculate some of it. We've also got to bring it all together. We've got to make sure that we do a sensitivity analysis, again something which Zoran was talking a little bit about in swarms. And that's what the VAMDC project is to do. So what Quantemol N, which was the original Quantemol, was meant to do was actually address this problem. Us poor as experimentalists have to work on a finite unit called the PhD student, which is 3 years, and how much cross-sections can they measure in a 3-year period? Well, never enough is the answer. So for what many data users need. So the idea was that Quantemol N would be able to calculate cross-sections for the things that we can't measure, or we can't measure quickly enough. The trouble is that most of those Quantemol calculations are at low energy. And was already said by Leon, we want to do things at higher energy. We want a plasma that goes from 0 to 1,000. And the R matrix won't let you do that. So you can, as Jonathan said at the beginning, use other techniques and models. And Quantemol is now building this in, particularly with our colleagues in India, Josh Pur, that should be Bobby Anthony and Vinod Kumar, to bring together both the R matrix calculation with higher energy calculations using more simple approximations. And I sort of just finished by showing you how that works and how Quantemol N, if you like, can be expanded. The solid black line, this is for ammonia, the solid black line is data calculated by the Quantemol. That's what you get if you buy the package at the moment. You'll be able to get those. And it will stop round about the ionization energy. What we then did was take the other methods, the high energy approximations, and run those. And they came out with these sort of lines here. And then the data, all these other stuff here is the experimental data. And what this shows is that if you combine these techniques, low and high energy, and here's another one which has got a resonance in it, so that's always a good test, you will see the Quantemol calculations are here, the scope calculations are coming in here. They actually agree quite well with the theory. They certainly are always within the experimental error bars, which never actually always match up. So what Quantemol will be able to do is estimate cross-sections for targets experimenters don't want to touch, particularly poisonous ones, or we can't do. It will produce all the calculations for radicals, and it will have a challenge. There are still remaining challenges, and one of the main challenges is how does Quantemol extend into big molecules, particularly things like chains of these molecules. And just because I always have to put Jonathan a challenge, the lighting industry, their favourite molecule is this one, diprosium triiodide, which has only got 500 electrons or something like that. So obviously, it's a bit of a challenge still for Quantemol to do. I'm going to keep this slide up, Jonathan, in every talk until you present me the cross-section, and then I'll take it down, okay? So that's just the people who have done the work. I hope what I've just tried to do is to show you that the Quantemol package is very important because of all the applications I showed. Just take away from lunch and think about all the applications we've got. Experiment's never going to be able to cover all those. Quantemol will get it right within most of the experimental error bars. And if we expand that on top to what Jonathan was talking about, the ionization energies and the higher energy calculations, that's pretty good for what the people need in most of those applications. And so it's a very powerful package. And we'll keep pushing it, and we'll keep doing it. And Jonathan ultimately will produce me diprosium triiodide as well. Thank you.